I am Wendelin Esguerra, AC 501, and I will be discussing integer linear programming. Integer linear programming including branch and bounds. Integer linear program is a linear programming with the additional requirement that one or more variables must be integer. The only difference that integer linear program has with the linear programming is that it has the constraint that one or more variables must be integer. LP relaxation of the integer program. The linear program that results from dropping the integer requirement. So, kung tatanggalin yung constraint na dapat yung variables ay integer, it will result to the LP relaxation of the integer program. Types of integer linear programming. First, all integer linear program, if all variables must be integer. For example, looking at the last constraint, x sub 1 and x sub 2 must be greater than or equal to 0 and integer. So, yung constraint na to, sinasatisfy niya yung non-negativity constraint tsaka yung integer requirement na dapat yung x sub 1 tsaka yung x sub 2 integer. Mixed integer linear program, if some but not all variables must be integer. Example, x sub 1 and x sub 2 must be greater than or equal to 0 and x sub 2 must be integer. So, dito, yung x sub 2 lang yung may requirement na dapat integer. Meaning, yung x sub 1, pwede siyang non-integer. Kaya, mixed integer linear program. Third type, 0 to 1 integer linear program. One or more integer variables are required to equal either 0 or 1. In many applications, 0 to 1 variables provide selections or choices with the value of the variable equal to 1 if a corresponding activity is undertaken and equal to 0 if the corresponding activity is not undertaken. Methods in solving integer linear program. First, graphical solution, and second, branch and bound. Graphical solution. Example, Eastbourne Realty has 2 million pesos available for the purchase of new rental property. After an initial screening, Eastbourne reduced the investment alternatives to townhouses and apartment buildings. Each townhouse can be purchased for 280,000 pesos and 5 are available. Each apartment building can be purchased for 400,000 pesos and the developer will construct as many buildings as Eastbourne wants to purchase. Eastbourne's property manager can devote up to 140 hours per month to these new properties. Each townhouse is expected to require 4 hours per month and each apartment building is expected to require 40 hours per month. The annual cash flow after deducting mortgage payment and operating expenses is estimated to be 10,000 pesos per townhouse and 15,000 pesos per apartment building. Eastbourne's owner would like to determine the number of townhouses and the number of apartment buildings to purchase to maximize annual cash flow. We begin by defining the decision variables as follows. T as the number of townhouses and A for the number of apartment buildings. The objective function in 1,000 pesos is maximize 10T plus 15A. 10T represents the 10,000 profit per townhouse and 15A represents 15,000 profit per apartment building. Constraints that must be satisfied. First constraint pertains to the funds available. 282T plus 400A must be less than or equal to 2,000. Kasi yung cost ng isang townhouse, 282,000. Tapos yung cost ng isang apartment building, 400,000. Tapos yung available fund lang nung Eastbourne ay 2 million pesos. Second constraint, 40 plus 40A must be less than or equal to 140. This pertains to the manager's time. So, 4 hours per townhouse per month, tapos 40 hours per apartment building per month. Tapos, meron lang 140 hours available yung manager. Then, the last constraint, T must be less than or equal to 5. Kasi yung townhouses na available for purchase ay 5 lang. So, yung townhouse na ipapurchase nung Eastbourne must be less than or equal to 5. The variables T and A must be non-negative. Yun yung non-negativity requirement ng linear programming. In addition, the purchase of a fractional number of townhouses and fractional number of apartment buildings is unacceptable. Thus, T and A must be integer. The model for Eastbourne Realty program is the following all-integer linear program. So, yung Eastbourne Realty problem, yung siya ay all-integer linear program. Kasi, yung townhouses tsaka yung apartment buildings na bibilin dapat ay whole number. Hindi naman pwedeng bumili ng kalahating townhouse lang or fractional part lang ng apartment building. So, yung all-integer linear program natin ay maximize 10t plus 15a, that's the objective function, subject to 282t plus 400a must be less than or equal to 2,000, 40 plus 40a must be less than or equal to 140, t must be less than or equal to 5, and t and a must be 0 and integer. Graphical solution using the graphical solution of an LP relaxation. Dropping off the integer requirements for T and A, and then solve using the graphical solution procedure. So, yung first step sa graphical solution, we need to omit the requirement that the variables must be integer. And then, graph no same procedure as a linear programming model. Let's take a closer look. We need to graph each constraint and shade the region where the three constraints meet. That's called the feasible region. From here, we get the best possible value of the objective function, which is also called the optimal solution. T equals 2.479 townhouses and A equals 3.252 apartment buildings. The optimal value of the objective function is 73.574, which indicates an annual cash flow of 73,574 pesos. We obtain this optimal value by substituting the value of T and A to the objective function. Unfortunately, Eastbourne cannot purchase fractional numbers of townhouses and apartment building. Further analysis is necessary. Rounding to obtain an integer solution. In many cases, a non-integer solution can be rounded to obtain an acceptable integer solution. For example, a linear programming solution to a production scheduling problem might call for a production of 12,954.4 cases of breakfast cereal. The rounded integer solution of 12,954 cases would probably have minimal impact on the value of the objective function and the feasibility of the solution. Indeed, whenever rounding has a minimal impact on the value of the objective function and constraints, most managers find it acceptable because a near-optimal solution is fine. However, rounding may not always be a good strategy. When the decision variables take on small values that have a major impact on the value of the objective function or feasibility, an optimal integer solution is needed. Example: LP relaxation resulted in T equals 2.479 townhouses and A equals 3.252 apartment buildings. Because each townhouse costs 282,000 pesos and each apartment building costs 400,000 pesos, rounding to an integer solution can be expected to have a significant economic impact on the problem. Suppose that we round the solution to the LP relaxation, obtain the integer solution T equals 2 and A equals 3, with an objective function value of 10 times 2 plus 15 times 3 equals 65. The annual cash flow of 65,000 pesos is substantially less than the annual cash flow of 73,574 pesos provided by the solution to the LP relaxation. How about other rounding possibilities? How about 2 equals 3 and A equals 3, or 2 equals 2 and A equals 4? Let us check. If we're going to use T equals 3 and A equals 3, let's substitute it to the objective function. 3 times 282,000 plus 3 times 400,000 equals 2,046,000. Let's use T equals 2 and A equals 4. 2 times 282,000 plus 4 times 400,000 equals 2,164,000. The rounded solution of these two possibilities is infeasible because Eastbourne's budget is only for 2 million pesos. Graphical solution of the all-integer problem. The graph of the feasible region is drawn exactly as in the LP relaxation of the problem. Then, because the optimal solution must have integer values, we identify the feasible integer solution with the dots shown in the figure. Instead of moving the objective function line to the best extreme point in the feasible region, we move it in an improving direction as far as possible until reaching the dot, providing the best value for the objective function. Let's take a closer look. Kung sa LP relaxation, yung optimal value natin ay yung pinakamalayo, which is yung pinaka-possible na malaking value. Dito sa graphical solution ng all-integer problem, lalagyan natin ng dots yung integers. Tapos, ibababa natin dun yung line, tas yung first dot na tatamaan ng line, siya yung optimal integer solution. Yung nakikita nga natin sa graph, number of townhouses, 4. Number of apartment buildings, 2. Yan yung optimal integer solution. The figure shows that the optimal integer solution occurs at T equals 4 townhouses and A equals 2 apartment building. The objective value function is 10 times 4 plus 15 times 2 equals 70, providing an annual cash flow of 70,000 pesos. This solution is significantly better than the best solution found by rounding, T equals 2, A equals 3 with an annual cash flow of 65,000. Branch and bound. The branch and bound approach is based on the principle that the total set of feasible solutions can be partitioned into smaller subsets of solutions. These smaller subsets can then be evaluated systematically until the best solution is found. When the branch and bound approach is applied to an integer programming problem, it is used in conjunction with the normal non-integer solution approach. The branch and bound method uses a tree diagram of nodes and branches to organize the solution partitioning. Characteristics of branch and bound. First, a node has two designated bounds, an upper bound and a lower bound. The upper bound is the z-value for the relaxed solution. The lower bound is the maximum integer solution or z-value for the rounded down solution. Notes: for integer linear programs involving maximization, the value of the optimal solution into the LP relaxation provides an upper bound on the value of the optimal integer solution. For integer linear programs involving minimization, the value of the optimal solution to the LP relaxation provides a lower bound on the value of the optimal integer solution. Last, the optimal solution will be between these two bounds. Steps of branch and bound method, generally for maximization. First, find the optimal solution to the linear programming model with the integer restrictions relaxed. Meaning, we're going to omit the constraint that the variables must be integer. Step 2. At node 1, let the relaxed solution be the upper bound and the rounded down integer solution be the lower bound. Step 3. Select the variable with the greatest fractional part for branching. Create two new constraints for this variable reflecting the partitioned integer values. The result will be two new constraints. Number 4. Create two new nodes for the two new constraints. Step 5. Solve the relaxed linear programming model with the new constraint added at each of these nodes. So when we're branching, every time we branch, we're going to add a new constraint. Number 6. The relaxed solution is the upper bound at each node, and the existing maximum integer solution at any node is the lower bound. Number 7. If the process produces a feasible integer solution with the greatest upper bound value of any ending node, the optimal integer solution has been reached. If a feasible integer solution does not emerge, branch from the node with the greatest upper bound. Last step, return to step 3 if the feasible integer solution does not emerge. For a minimization model, relaxed solutions are rounded up, and upper and lower bounds are reversed. Example: the owner of a machine shop is planning to expand by purchasing some new machines, presses, and lathes. The owner has estimated that each press purchase will increase profit by 100 pesos per day, and each lathe will increase profit by 150 pesos daily. The number of machines the owner can purchase is limited by the cost of the machines and the available floor space in the shop. The machine purchase prices and space requirements are as follows. The owner has a budget of 40,000 pesos for purchasing machines and 200 square feet of available floor space. The owner wants to know how many of each type of machine to purchase to maximize the daily increase in profit. The linear programming model for an integer programming problem is formulated in exactly the same way as the linear programming. The only difference is that in this problem, the decision variables are restricted to integer values because the owner cannot purchase a fraction or portion of a machine. The linear programming model follows. Maximize 100x sub 1 plus 150x sub 2 subject to 8,000x sub 1 plus 4,000x sub 2 must be less than or equal to 40,000 pesos. Constraint number 2, 15x sub 1 plus 30x sub 2 must be less than or equal to 200 square feet. And x sub 1 and x sub 2 must be greater than or equal to 0 and integer. where x sub 1 is equal to the number of presses and x sub 2 is equal to the number of lathes. The decision variables in this model are restricted to whole machines. The fact that both decision variables x sub 1 and x sub 2 can assume any integer value greater than or equal to 0 is what gives this model its designation as a total integer model. Step 1. Find the optimal solution to the linear programming model with the integer restrictions relaxed. We can see our integer linear program model. Maximize 100x sub 1 plus 150x sub 2 subject to these two constraints and another constraint restriction x sub 1 and x sub 2 must be greater than or equal to 0 and integer. For this model to be relaxed, we need to omit the word integer. We need to omit the restriction that the variables must be integer so we can solve the integer linear programming model. So, it only satisfies the non-negativity constraint and not the integer constraint. Let's solve this problem using the Excel solver because we're going to compute so many linear programming models later on. So, we need to use the solver to make the problem easier. Using Microsoft Solver, first, enter the coefficient of the objective function, here in profit per unit. X sub 1 will produce 100 pesos per unit and x sub 2 will produce 150 pesos per unit. Second, enter the coefficient of constraints 1 and the right-hand side value. So, constraint number 1 is 8,000 x sub 1 plus 4,000 x sub 2 must be less than or equal to 40,000. Third, enter coefficient of constraint 2 and the right-hand side value. Constraint 2 is 15x sub 1 plus 30x sub 2 and the right-hand side value is 200 square feet. For the objective function, here, the objective function, enter the formula for computing the z. So what's the formula for computing the maximize problem? Sum product of the profit per unit multiplied by the optimal solution. We can see that the optimal solution value views 0 because there is no value yet for x sub 1 and x sub 2. Step number 5, enter the formula for the left-hand side of the constraints. So, the left-hand side of constraint 1 should be less than or equal to 4,000. 8,000 multiplied by x sub 1 and 4,000 multiplied by x sub 2, the answer must be less than 40,000. So, let's enter the formula. Sum product of the coefficient of constraint 1 and the value of x sub 1 and x sub 2. Next, for the formula of constraint 2, sum product of the coefficients of constraint 2 and the value of x sub 1 and x sub 2. Let's enter the right hand side value. For x sub 1, 40,000. For constraint 1, 40,000 rather. For constraint 2, 200. Using the solver, let's set the objective function, that is the optimal solution value. Maximize, then by changing variable cells, that's x sub 1 and x sub 2. And then we need to add the constraints. This left hand side must be less than or equal to 40,000. Left hand side of constraint 2 must be less than or equal to the right hand side of constraint 2. And then we need to click solve so that we can get the answers we need. From here, we can see that the value of this integer linear program results in x sub 1, 2.22, and x sub 2, 5.56, if we're going to round it into decimal places. And the optimal solution value resulted to 1,055.55. Here. Going back to our presentation, x sub 1 equals 2.22, x sub 2 equals 5.56, and our C value equals 1,055.56. Step 2. At node 1, let the relaxed solution be the upper bound and the rounded down integer solution be the lower bound. So, first, upper bound. Ito yung na-compute natin kanina using the Excel solver. And then, lower bound, we're just going to round off the values of x sub 1 and x sub 2 and then substitute it to our objective function. So, the rounded value of 2.2, please take note, in maximization problems, we are going to round down the values, while in minimization problems, we are going to round up the values. So here, for a maximization problem, let's round down 2.22, that will result to 2, and x sub 2, let's round down 5.56, that will result to x sub 2 equals 5. So, substituting it to our objective function, we will get an optimal solution of 950. So, our upper bound will be the 1055.56, which we get from solving the linear programming as relaxed, and the lower bound will be the rounded down integer solution. So here we can see the upper bound is 1055.56 and the lower bound is 950. Step 3. Select the variable with the greatest fractional part for branching. Create two new constraints for this variable reflecting the partitioned integer values. The result will be two new constraints. So here we can see Yung upper bound natin, yung x sub 1, 2.22, and the value of x sub 2 equals 5.56. The 0.56 portion of 5.56 is the greatest fractional part. Thus, x2 will be the variable that we will branch on. So, kung anong variable yung may fractional part na pinakamalaki, dun tayo magbabranch. Because x sub 2 must be an integer value in the optimal solution, the following constraints can be developed. X sub 2 should be less than or equal to 5, or x sub 2 should be greater than or equal to 6. This constraint simply says that x sub 2 cannot be a value between 5 and 6. In other words, x sub 2 can be 0, 1, 2, 3, 4, 5, or 6, 7, 8, but it cannot be a value between 5 and 6, such as 5.56. That's why we're making these constraints to make the values of the variables integer. Step 4. Create two new nodes for the two new constraints. So, our first node, it has an upper bound of 1055.56 and the lower bound of 950. So, we are going to branch from these two nodes using x sub 2 equals 5.56. Node 2. With the first constraint that x sub 2 must be less than or equal to 5. The third node represents that x sub 2 must be greater than or equal to 6. Step 5. Solve the relaxed linear programming model with the new constraints added at each of these nodes. So again, we're going to solve a linear programming model. So first, let's solve node 2. With the objective function and the new constraint added, x sub 2 must be less than or equal to 5. Now we have three constraints. So we're going to solve this in our Excel solver. We just need to add our new constraint, constraint 3. With the right-hand side value of 5. Then we're going to assign this constraint 3 equal to first we need to delete our previous solution. So this will be 0 again, the optimal solution value and the optimal values of x sub 1 and x sub 2. We need to assign constraint 3 to x sub 2 here. And then let's add this to our solver. We just need to add an additional constraint. X sub 2, or constraint the left hand side of the constraint number 3 must be less than or equal to the right hand side. And then solve. From here, we get an optimal value of x sub 1 as 2.5 and x sub 2 as 5, and we get an optimal solution value of 1000. The optimal solution for this model with integer restrictions relaxed is x sub 1 equals 2.5, x sub 2 equals 5, and c equals 1000. Now, let's solve for node 3. We can see that node 3's third constraint is x sub 2 must be greater than or equal to 6. So, let's solve this problem with this new constraint. So, let's erase this. The right-hand side is 6. Using the solver, let's change this constraint. Constraint 3, left-hand side must be greater than or equal to the right-hand side. Okay, now let's solve. From here, we get the value of x sub 1 as 1.33, the value of x sub 2 as 6, and the optimal solution value as 1033.33. The optimal solution for this model with integer restrictions relaxed is x sub 1 equals 1.33, x sub 2 equals 6, and z equals 1033. Step 6. The relaxed solution is the upper bound at each node, and the existing maximum integer solution at any node is the lower bound. So, from our previous branch and bound diagram, we will add the upper bound and the lower bound. So, the upper bound of the node 2 is the optimal solution we get from solving this linear program, adding this constraint, x sub 2 must be less than or equal to 5. So the upper bound is 1000 and the lower bound remains as 950. While in node 3, our upper bound is 1033 and our lower bound is 950. Step 7. If the process produces a feasible integer solution with the greatest upper bound value of any ending node, the optimal integer solution has been reached. Meaning, magsa-stop lang tayo kung yung upper bound value natin ay may variable siya na parehas integer. Doon natin malalaman na we need to stop because we already reached the optimal integer solution value. If a feasible integer solution does not emerge, branch from the node with the greatest upper bound. So, kung wala namang ganon, yung x sub 1 and x sub 2, hindi pa sila parehas integer, kailangan pa nating mag-branch. So, saan tayo magbabranch? Doon tayo magbabranch sa node with the greatest upper bound. And then, we're going to return to step 3. So, from here, makikita natin na ang node na may greater upper bound ay yung node 3. Meron siyang 1033 na upper bound. Continue to branch at the node with the maximum upper bound. In general, always branch from the node with the maximum upper bound. The steps for branching are repeated. So, makikita natin sa branch and bound diagram natin, wala pa tayong variables na parehas integer. Kasi, yung sa node 2, yung x sub 1, 2.5 pa. Tapos, yung sa node 3, yung x sub 1, 1.33 pa. So, magbabranch tayo. Magbabranch tayo doon sa node na may mas malaking upper bound, which is node 3. So, we will branch from node 3. Tapos, repeat lang natin yung steps 3 to 6. Select the variable with the greatest fractional part for branching. Create two new constraints for this variable, reflecting the partitioned integer values. The result will be two new constraints. The variable that has the value with the greatest fractional part is selected. Because x sub 2 has an integer value, x sub 1 with a fractional part of 0.33 is the only variable we can select. Thus, two new constraints are developed from x sub 1. X sub 1 must be less than or equal to 1, and x sub 1 must be greater than or equal to 2. Meaning, yung x sub 1, yung value niya pwedeng 0, 1, 2, 3, 4, 5, pero hindi pwedeng yung value niya ay between 1 and 2. Step 4, create 2 new nodes for the 2 new constraints. So, magdadagdag tayo ng dalawang nodes mula doon sa node 3. Yun ay node 4 tsaka node 5. Yung node 4, may constraint na x sub 1 must be less than or equal to 1. Tas yung node 5, may constraint na yung x sub 1 must be greater than or equal to 2. Next, solve the relaxed linear programming model with the new constraints added at each of these nodes. So, magsasolve ulit tayo ng linear programming. Gagamit ulit tayo ng solver ng Excel. Pero makikita natin sa model ng node 4, yung kaninang model ng node 3, same constraints, tatlo, dadagdagan siya nung constraint ng node 4 na yung x sub 1 must be less than or equal to 1. Huwag natin kakalimutan na yung constraint kung saan tayo nag-branch, andun pa rin siya. Yung constraint ng node 3 na yung x sub 2 must be greater than or equal to 6. Tapos, idadagdag lang natin yung constraint nung node 4. Bali, magkakaroon ng dalawang additional constraint dun sa pinaka-original linear model natin. Tapos, isosolve natin yan using the solver. So, burahin lang natin yung solution kanina. Tapos, magdagdag tayo ng additional constraint kasi makikita natin, 4 na yung constraint. So, constraint 4. Ang right-hand side value niya ay 1. Tapos, yung left-hand side ay equal to x sub 1. So, using the solver, dahil yung huling solution natin kanina ay using node 3, tapos sa node 3 din tayo nag-branch, magdadagdag na lang tayo ng additional constraint na yung constraint 4 na x sub 1 must be greater than, must be less than rather, or equal to 1. Okay. Then, solve. Makikita natin na yung binigay sa atin na solution, yung x sub 1, ang value niya ay 1, yung x sub 2, ang value niya ay 6.17, tsaka yung optimal solution value ay 1,025. The optimal solution for this model with integer restrictions relaxed is x sub 1 equals 1, x sub 2 equals 6.16, and the z value is equal to 1,025. Tapos, let's solve naman the solution at node 5. So, still, nandito pa rin yung constraint na mula sa node 3 that x sub 2 must be greater than or equal to 6. Tapos, yung constraint from node 5 na x sub 1 must be greater than or equal to 2. Tapos, isa-solve natin. So, burahin lang yung solution kanina. Then, yung constraint 4, papalitan natin. 2 yung right-hand side niya. Tapos, papalitan din natin yung constraint na yon. Constraint 4, the left-hand side must be greater than or equal to the right-hand side. Okay. And then, solve. Makikita dito, sabi, solver could not find a feasible solution. Solver cannot find a point for which all constraints are satisfied. Yun yung sabi ng solver. So, meaning, yung node 5, infeasible siya. However, there is no feasible solution for this model. Therefore, no solution exists at node 5. The relaxed solution is the upper bound at each node and the existing maximum integer solution is the lower bound. So, yung nodes natin kanina na 4 and 5, lalagyan natin siya ng lower and upper bound. So, yung node 4, yung upper bound niya ay 1,025, tas yung lower bound niya 950 pa rin. Tas yung variables ng upper bound, x sub 1 equals 1, tas yung x sub 2, 6.16. Tapos, yung node 5, dahil wala nga solution, infeasible siya. Continue to branch at the node with the maximum upper bound. Kasi, wala pa rin tayong optimal integer solution. Wala pa rin variables na parehas ay integer. So, magbabranch pa tayo. Doon tayo magbabranch siya. May maximum upper bound. Ngayon, yung endpoints ng branch and bound diagram natin ay 2, 4, and 5. Kasi sila pa yung dulo. Yung 2, 1,000 yung upper bound. Yung 4, 1,025, while 5 is infeasible. Since a solution does not exist at node 5, there is no comparison between the upper bounds at nodes 4 and 5. Comparing nodes 2 and 4, we must branch from node 4 because it has the greater upper bound. So, gagawa ulit tayo ng constraint. Next, since x sub 1 has an integer value, x sub 2 with a fractional part of 0.17 is selected by default. The two new constraints developed from x sub 2 are yung value ng x sub 2 ay 6.17. Hindi naman pwede na may decimal. So, magkakaroon tayo ng constraint na yung x sub 2 must be less than or equal to 6 or x sub 2 must be greater than or equal to 7. Tapos, gagawa natin ng nodes yung dalawang constraints na yon. Kita nyo, nag-branch tayo sa node 4. Tapos, nagkaroon ng node 6 na may constraint na x sub 2 must be less than or equal 6. And then, node 7 with a constraint that x sub 2 must be greater than or equal to 7. Then, we're going to solve the relaxed linear programming model with the new constraint added at each of these nodes. So, ito yung original linear program model natin. Tas, ito yung constraint na nagmula sa node 3, constraint na nagmula sa node 4, tapos constraint na sa node 6. Kasi solution ng node 6 yung sinosolve natin. Huwag natin kalimutan na yung constraints habang nagbabranch, cumulative siya. Tas, isosolve na natin. Yung constraint 4 natin ay 1. Tapos, magdadagdag tayo ng additional constraint. Constraint 5. With the right-hand side value of 6. Tapos, yung left-hand side value niya ay equal to x sub 2. Tapos, dadagdag lang natin yung constraints. Tatanggalin natin yung fourth constraint kanina kasi galing yon sa node 5 and nagbabranch tayo sa node 4. So, constraint 4 must be less than or equal to 1 dun sa right-hand side. Add. Tapos, constraint 5, left-hand side of constraint 5 must be less than or equal to the right-hand side. Okay. And then, we're going to solve. So, dito sa model na to, ang binigay niya sa atin ay na value ng x sub 1 ay 1 at value ng x sub 2 ay 6 with an optimal solution value of 1,000. The optimal solution for this model with integer restrictions relaxed is x sub 1 equals 1, x sub 2 equals 6, and z equals 1,000. Tapos, yung node 7 naman. Yung node 7, papalitan lang natin yung constraint number 5. Yung right-hand side niya ay 7. Tapos, papalitan natin yung constraint dito sa solver. It must be, x sub 2 must be greater than or equal to 7. Okay, then we'll solve. Sabi ng solver cannot find a point for which all constraints are satisfied. Meaning, walang solution dito sa node 7. Kaya, infeasible siya. So, tingnan na natin yung diagram natin. Lalagay natin yung upper bound and lower bound no node 6. The upper bound is 1,000 with variables x sub 1 equals 1 and x sub 2 equals 6. Tas yung lower bound niya din ay 1,000 with a variable x sub 1 equals 1 and x sub 2 equals 6. Tapos yung node 7, infeasible. So, na-reach na natin yung optimal integer solution natin. The value of 1,000 at node 6 is the maximum or upper bound integer value that can be obtained. It is also the computed lower bound because it is the maximum integer solution achieved to this point. Thus, it is not possible to achieve any higher value by further branching from node 6. A comparison of the node 6 solution with those at nodes 2, 5, and 7 shows that a better solution is not possible. The upper bound at node 2 is 1,000, which is the same as that obtained at node 6. Thus, node 2 can result in no improvement. The solutions at nodes 5 and 7 are infeasible, and thus further branching will result only in infeasible solutions. By the process of elimination, the integer solution at node 6 is optimal. In general, the optimal integer solution is reached when a feasible integer solution is generated at a node and the upper bound at that node is greater than or equal to the upper bound at any other ending node. In the context of the original example, this solution indicates that if the machine shop owner purchases 1 press and 6 slates, a daily increase in profit of 1,000 pesos will result. And that concludes my report. Thank you for watching.